Hey everyone, this is Professor Chan for Math 1245 speaking. Today we're going to be going over section 3.5, which is properties of rational functions and graphing rational functions. Okay, this will probably be split into two different videos. So the first one, I just want to kind of go over basics and specific terminology. It's not going to make too much sense to you guys, and it's probably going to feel I guess a bit aimless, where it feels like you're just memorizing random terminology. But the second part of 3.5 is going to make more sense later on. Okay, so let's talk about properties of rational functions. And idea is, remember, what is a rational function? A rational function essentially is a fancy fraction. Okay, and what it is essentially is, instead of a number over a number, it's a polynomial over another polynomial. Okay, so one of the things is you will be asked to find a domain of a rational function. Okay, and that's pretty straightforward. So all you have to do is set the bottom equal to 0, right? So here, right, I can set the bottom equal to 0. I can set x plus 3 is equal to 0. And I have x equals -3, right? And if you think about my domain, we would say is x such that x is not equal to -3. Okay? Okay. So, same thing. We'll do this bottom one right here. And what I can do is I can factor this one. This is x plus 2 times the quantity x plus 3, and I can set that equal to 0. I have x plus 2 is equal to 0, and I have x plus 3 is equal to 0. X is equal to -3. X is equal to -2. So I would say my domain is x such that x cannot equal to -2 and -3. Okay? So to find domains of rational functions is pretty straightforward. All you have to do is just set the bottom part equal to 0 and solve for x. Okay? And remember, why do these values not work? Remember that if you plug these numbers back into the denominator, right? If, for example, this very first problem, if I plug -3 back into my equation, I will have 0 on the bottom, and I can't divide by 0. Okay? For the following. Okay? And let's take a look at one more example. Okay? Even if, so let's take a look at this. Even if I have the top and I factor this, and it cancels out, I still will set the bottom equal to 0. So my domain will still be x such that x cannot equal to -2. Okay? For the following here. Okay. Okay. And then just one other thing too, right? So if I'm graphing 1y over 1 over x squared, it's going to look something like this. Okay. So I have a vertical asymptote at y is equal to 0, and I have a horizontal asymptote at x is equal to 0. Okay? For the following here. Okay, so right, that means I have an invisible fence at y is equal to 0. And I have an invisible fence at x is equal to 0. And remember, asymptotes means, right, it's a line in which your graph can never touch or cross for the following. Okay, so there's two types of, remember, rational graphs, right? We have 1 over x, and then we have 1 over x squared. Okay. Let's see. Okay, so we're going to talk about different attributes of a rational function. Okay, so the first thing I want to talk about is what's called vertical asymptotes. Okay, so before we find vertical asymptotes, what we're going to do is we are going to factor and cancel in lowest terms. Okay, yeah. And then things that cancel out will be what's called a whole. Okay, so let me show you an example like this right here. Sorry. So I have x cubed minus 8 all over x squared minus 5x plus 6. Sorry. So what I'm going to do is I'm going to factor the top fraction and the bottom fraction, right? So remember how to factor x cubed minus 8. This is cubic. This one is x minus 2. And then my other factor is x squared plus 2x plus 4. Okay. And then when I factor the bottom one, this is x minus 2 times the quantity x minus 3. Okay. So I'm going to cancel this right here. Okay. So my canceled one is called a whole. So I'm going to set x minus 2 is equal to 0. And I have x is equal to 2. Okay. And then I can plug this into my reduced fraction, right? So actually, let me reduce my fraction and rewrite this here. Okay. So if I plug f of 2 in, do not plug it into your original, plug it into your reduced form. This will be 2 squared plus 2 times 2 plus 4 all over 2 minus 3. 4 plus 4 plus 4, and negative 1. This equals a negative 12. So the idea is I have a whole at 2, negative 12. Okay, this is going to make more sense later on. But the idea is there will be an actual literal whole, or there'll be an open circle at that specific point. Okay. So things that cancel out, you'll plug it into your reduced form, and that's called a whole. Things that will not cancel out, you're going to look at the bottom part, like what we did earlier, right, in the first page. So I'm also going to be finding my domain. So I'm going to set x minus 3 equals 0. And I have x is equal to 3. And so I have a vertical asymptote. We do VA for short at x is equal to 3, right? So the idea is if I graph this, okay, I have no idea what my function will look like, but if I graph this here at 1, 2, 3, right, I have a invisible fence right here, and at 2, negative 12, right, I'll have a hole right here, okay? I have no idea what the rest of my graph is. Maybe it'll look something like, who knows, something like this, okay? For the following here, okay? So yeah, once again, holes are canceled factors that you set equal to 0, and then you'll plug in to find your y. Your vertical asymptote is your denominator factors after that remain after the cancellation portion. Okay. Okay. So first two aspects, right, we have is vertical asymptotes and holes. Okay. So now let's talk about the next part, in which we have a horizontal asymptote. Okay. So horizontal asymptotes is the following. there are actually many cases. There's actually 4 cases in dealing with horizontal asymptotes, okay? When we look at what's called a horizontal asymptote, right? Remember, horizontal asymptote is it's kind of a horizontal fence, okay? So this is when x approaches infinity and x approaches negative infinity, okay? So let's talk about the very first case here. So the first case is if the degree in your numerator is smaller than the degree in the denominator, right? So the bottom degree is larger than the top degree, right? So if we look at this one here, sorry, this is not x equals, it'll be y is equal to 0, okay? So yeah, if my degree on the bottom is larger than the degree on top, I will have a horizontal asymptote as y is equal to 0, right? So if I look at this here, okay, I'm going to have, right, the bottom degree is degree of 3, bottom of the degree is degree 3, the top degree is degree of 1. Okay. So let's talk about why that's true, okay? So let's talk about this, right? So let me show you. So let me graph, okay? I'm going to graph the top one, which is x, and on the top, and I'm going to graph the bottom one, which is x cubed plus 8, okay? So let me explain to you why that's true, right? So why is it that I'm going to have a horizontal asymptote at y equals 0? So remember, when we analyze asymptotes for horizontal, we look at as x approaches infinity, okay? So if you look at this here, right, so y1 is x, and right, notice as I'm going up, right, x is 7, 8, 9, 10. But if you look at x cubed, or what my second one, which is x cubed plus 8, notice it's growing a lot quicker. And since we're dividing, right, so if we go back up, right, so yeah, if you look right here, right, so the idea is when x is 1, I have 1 divided by 9, but then I'll have 2 divided by 16, 3 divided by 35, and so forth. So my y value is getting a lot smaller, and as you can see, it's going to essentially get closer to 0, right? Because 20, like example, 25 divided by 15,633, that's a really tiny number, okay? And I can actually show this to you too if I just graph the whole thing. So you can see this if I graph it, and you can kind of see it immediately. Now, your calculator kind of tricks you, but idea is notice as you're going on, you can see that it's getting closer and closer to 0, okay? And you can also tell too by the second graph. So if you look at your y value, right, so 0.111, and notice as I'm going to this, right, it's getting smaller and smaller and smaller, it's getting closer to 0, okay? And you can actually also go the other way. So if you notice, if you're going from the other side, as x approaches negative infinity, it's also getting smaller and smaller and smaller, okay? So yeah, so you can see that it's flattening out for the following here, okay? One thing too is if you're not sure, you can plug in large numbers. So for example, like we're like, well, what happens when x is 10, right? It'll be 10 over 1,008. That's really tiny. If I plug in 100, I'll get 100 over 1,000,008. So it's gonna get smaller and smaller as my x value gets larger in both directions. Okay, so let me show you the second case right here. So let's talk about this. Well, what will happen if your numerator is the same degree as your denominator? Okay, you'll have the same horizontal asymptote as y equals to whatever number you have. Okay. So I'm going to kind of show you a couple of different ways about this, okay? Okay, so actually, why don't we do this? Let me graph both of these. I'm going to graph the first one, right? So I have x squared plus 5x plus 6 divided by 4x squared minus 9. Okay, so let's look at what happens as I'm tracing as I keep going towards the right. So it's constantly decreasing, but what's going to happen is actually going to flatline. Let me kind of show you quickly. So let's say if I'm going up by 10. Notice it actually converges, okay? It gets closer and closer, and it actually is going to get really close to 0.25, okay? As you can see right here, okay? So my horizontal asymptote is equal to, is going to be the following. It's going to be y is equal to 0.25, or y is equal to 1/4, okay? And the same will hold true if I go in the opposite direction, right? So if I go all the way up, sorry, let's just start at 0. And you can see, you know, it's starting to get closer and closer to 0.25 as I go the other way. Okay? Okay. So let me graph the second one right here. So I have here 3x squared plus so second graph. Let's look at what's happening here. Sorry, let me start off at 0. So if I look at my table, look at my y values, it's getting closer and closer to 3. Okay? Now if I go to the opposite direction, so if I start at 0, notice it also gets closer and closer to 3. Okay? Yeah, notice and notice too, as you get closer to infinity or negative infinity, right? As you approach that, notice it starts to kind of taper off. Like it's not decreasing or increasing as quickly. So you can kind of tell that's starting to converge. Okay. So this one, I have a horizontal asymptote at y is equal to 3. Okay. Now, I know some of you guys aren't really the best at like kind of looking at your calculator and be like, how do I know where it's approaching? It's kind of hard. Okay. So here's a trick, right? So remember, this is if they have the same degree, both numerator and denominator, right? Because both of these have, right? Both of these have a degree of 2, right? Both of these also have a degree of 2, okay? So the idea is, think about if you're plugging large numbers in. This right here is kind of irrelevant, right? Same thing here. This part's irrelevant because the x squares are going to grow the fastest. So the idea is, if I look at this, right, I have x squared over 4x squared, and that reduces to 1/4. Okay? And then here, if I have 3x squared over x squared, that reduces to 3. So as you can see, right, all I do is I look at my first terms for each of my numerator and my denominator, and then I can reduce it, and then that number is my horizontal asymptote for the following here. Okay. Now, if you don't like that way, you can also use long division. Okay, so let me show this. Right, so if you're not sure what your horizontal asymptote, you can also do long division. Example here. I take my top and divide by the bottom. So you can do x squared times x squared. Well, I multiply x squared to get to 3x squared. That'll be 3. My bad. And this will be 3x squared plus 9x plus 15. And I'll subtract it. And this is negative 7x minus 12. Okay. So I have y is equal to 3 minus 7x minus 12 over x squared plus 3x plus 5. Okay. Now the thing I want to realize is this. Remember, based off of rule 1, or case 1, remember if your degree on the bottom is larger than the degree on top, it goes to 0. Right? This is based off of case 1. So this is essentially irrelevant. This goes to 0, and that's why I have a horizontal asymptote of y is equal to 3. Okay. And then let me show you the other one really quickly as well, right? So we can also get do long division. We should get 1/4 as well. So I'll do x squared plus 5x plus 6 all over 4x squared minus 9. And this is 1/4. So I multiply both of these by 1/4. So this is going to be x squared plus 0x. And this is negative 9/4. I subtract this. I'm left with 5x plus 33 over 4. So I have y is equal to 1/4 plus 5x plus 33 over 4 all over 4x squared minus 9. And then this goes to 0. Okay. So that is horizontal asymptote for the second case. So first case, if your degree on the bottom is larger than the degree on top, it goes to 0. If they're the same degree, if your highest degrees for both is the same, you just have y equals a number. So you're always just looking at the coefficients, okay? And you can also use long division as well. Okay. So let's look at the third case. What happens if your degree is, for the numerator, is greater than degree by 1, right? So if I look at this here, okay, this will be degree 2, right? And then this here will be degree 1. So I can also use long division. So I'm like, what will multiply x by to get to x squared? I'll put x up. This is x squared minus 3x minus, and so I have 10x plus 8. Okay, and I could do plus 10. So this will be 10x minus 30, and then I'll subtract. This will be 38. So I have y is equal to x plus 10 plus 38 over x minus 3. Now, once again, remember that if the degree is larger on the bottom than it is on top, right, this goes to 0. So I have an oblique at y is equal to x plus 10. That is my oblique asymptote. Okay. Now, some of you guys are wondering, what does oblique mean? Okay. all oblique means is this. Oblique is essentially a line that's not horizontal or vertical, so it has some form of slope, right? So ideas of an oblique asymptote will look something like kind of a diagonal looking line, okay? That's all oblique means, okay? And so remember, it is, sorry, so let me erase this right here. But the definition for oblique, or the criteria for oblique, is if your numerator is greater than the degree of the denominator by only 1, okay? Okay. Remember this too. So just remember this too. If you are trying to find oblique, you could do synthetic, okay? Now we're lucky because we're dividing by just x minus a number. Remember, if you divide by x plus or minus a number, you can do synthetic division. But if you're dividing by like x squared, x cubed, you can't do that, okay? But remember, right, we can do synthetic, where I plug in 3. I have 1, 7, 8. I do 1 times 3 is 3. 10 plus 3 is 30. So I have 38, but I'm focused on this. This is y is equal to x plus 10. So that is my oblique asymptote here. Okay. Now let's talk about the very last case. Okay. If your numerator is greater than the degree by more than 1, okay? So, for example, this one here, right? I have degree of 5 and I have degree of 1, right? So you can see 5 minus 1 is 4, so it's greater than by 4, right? Which is more than 1. Okay, so let me backtrack. Let's talk about this, right? So case 3 is if the degree on top is greater than the degree on the bottom by just 1. But if it's more than 1, we will not have an oblique asymptote. In fact, we will have no asymptotes, okay? So that's actually nice. So if you know it's larger by more than a degree of 1, then we don't have to worry about that, okay, for the following here. Okay. So let's talk about all the parameters for rational functions. So you need to find the domain. You need to find if it has holes, if it has vertical asymptotes, and then you also want to find whether it has horizontal or oblique asymptotes. So let's talk about the 4 cases. Let's summarize. So if degree on the bottom is greater than degree on top, you'll have a horizontal asymptote of y is equal to 0. If you have a degree on top that's the same as the highest degree on the bottom, then you'll have y equals the constant. So remember, what you do is you look at the numbers in front of it, and then you simplify that, or you can do long division and then go from there. If the degree of the numerator is greater than the degree of the denominator by just 1, you'll have an oblique. And then if the degree of the numerator is greater than the degree of the denominator more than 1, then you'll have no asymptotes at all. Okay? Okay, so I know there's a lot to take in, okay, but it's going to make more sense as we kind of move along, okay? The second video is going to be more application. It's going to make more sense, okay? But other than that, I will see you guys later.